Similar title is Specialized System Solvers for Very Large Systems, Theory and Practice. Okay, so I don't want to worry about that. So the question that we want to discuss today is a very simple one, classic problem, right? It goes way back, and that is, given a linear system, how do you solve that system quickly, right? So this is a fundamental subroutine for a lot of problems. Unfortunately, we really don't know how to do this. But what I will do today is talk about a very special kind of linear system for which we've made a lot of headway and why that's good enough. Okay?
What does it mean we don't know how to do this?
Sorry?
What do you mean we don't know how to do this?
Well, we don't know how to do them in the speeds we'd like, right?
Oh.
So in fact, like n cubed time, it's just not efficient, right? So in our day, when we were as young as everyone else in the audience, right, n cubed was a reasonable amount of time, right? You had a few thousand variables, and a cube of that was reasonable, right? Now, a modern system for people much younger than myself is 1 billion variables, right? So those are the kind of numbers that's right for you. And probably by the time you're my age giving this talk, 1 billion will be seen very small, right? And unfortunately, the trouble is when you cube those kind of numbers, you get big numbers, right? It doesn't matter, right? Okay, so that's the problem, right? So an easy case is lower triangular systems. So we know how to do that in linear time, and so the goal is to get algorithms that run in that amount of time, right? Okay, so throughout this we'll assume that our matrix is symmetric, positive definite. Let's see. So the question is, can we get speeds like that for this case? Okay. So there's a, so this is, unfortunately, I'm not sure what happened here. Okay, so let me just do something quickly here. Sorry. So that's the problem. I should have realized that. I'm sorry. Couldn't figure out why that used. Sorry.
Interesting screensaver.
Yeah, so what the heck happened here? Oh, here we go. Okay, let me give you a different talk. Okay, that's a good start. Okay, so it's almost the same time. Right? Okay. So anyway, so let's go here. So do that.
I think it's a first.
So we had a false start there. So a whole new talk. So we finished that talk. We're on to talk 2.
Is that cube still not okay?
Yeah, hold on. That's good. So spectrograph theory is the interplay between graph theory. So what I'd like to do is use graph theory to solve linear algebra problems and use linear algebra to solve graph theory problems. Okay? And so this area, at least for me, we've been working on this for 20 years. It sort of started with some work of Praver and Vaidya in 1991. Used graph theory for iterative system solvers. And this sort of changed the whole mindset of how we would go about solving linear systems, right? And after 20 years, this has blossomed into a whole beautiful area, which I'd like to go through with you. Okay? So again, we want to solve a linear system.
Same one, but
the same linear system. It's been around forever, right? And, right? So today what I'd like to do is solve a special case called graph Laplacian. So what's a graph Laplacian? It's, you take a, went too fast. So for us here, we have symmetric diagonally dominant systems. Okay. So what we want to do here is we'll say that a matrix is Laplacian if the off-diagonal entries are non-positive, if all the row sums and column sums are 0. Okay. A more general case is what's called symmetric diagonally dominant, which simply says that if you take any entry on the diagonal, AII, it should be greater than or equal to the sum of the absolute value of the off-diagonals. And you can show, Grimbaum and I showed that, in fact, you can reduce symmetric diagonally dominant to solving graph Laplacians. Okay, so let's define what's called a graph Laplacian. What you do is you take your favorite weighted graph, non-negative edge weights, and what you do then is you make up an incidence matrix, you make up a diagonal degree matrix, and you simply subtract the degree matrix from the incidence matrix from the diagonal matrix. Okay, so another way to think of it here is if you have a graph on the left, you can make a matrix out of it by simply taking the edge weights, negating them, and putting the degrees down the diagonal, right? So in general, from the rest of the talk now, we'll not talk about linear systems anymore. We'll just talk about graphs, right? Good. Okay. So there's so there's a long history of solving graph Laplacians. Vijay then in his original paper gave for the planar case a runtime of n to the 1.2. We were able to extend this at certain ideas, so n to the 1.5 for 3D graphs. So a major breakthrough was the Spielman-Tang paper in 2004, where they gave n to the log 15 n power. The 15, I think, I'm not sure anyone's actually calculated. Other theory was 25 logs. Not clear how you ever have that many logs in a runtime, but it took 80 pages to get that many logs. But anyway, so it's an interesting question, but still, philosophically, it's a big deal, because now all of a sudden it says that, in principle, it's linear time to solve these systems, right, up to a few logs. Okay? So we were able to get rid of all the logs in the planar case, and then with Costas and Pang, we got it down to 2 logs, with ignoring some log-log factors and some other low-order terms. And more recently, we got it down to a single log. So let me just explain in more detail what these system solvers do then. So your input then is a linear system, symmetric diagonally dominant. And in this case, what you're trying to do then is get an approximation to your linear system in what's called the A norm. The other thing here is you have a term here, which is that it's an iterative method, so you don't actually get the exact answer, but the error then is log 1 over epsilon. So again, you have another term depending on the quality of the answer you want. So now what I'd like to do is convince you that you actually want to solve graph Laplacians by giving you some applications. So the simplest classic application to think about is that you view the edges as conductors, say electrical or heat, doesn't matter. If you do it as electrical, then you view V as a column vector of voltages. When you multiply the graph Laplacian times V, you get back residual currents at the nodes. So another way to think of it is if you're given residual currents at the nodes of a graph, and you solve for V, this gives you the voltages that you would get if you inject those currents into the nodes. Okay? So this is where these come up. Okay? So when this comes up, say, if you have an integrated circuit, in this case, what you do is you're injecting heat, and you have heat sources and sinks throughout the circuit. And what you'd like to do is determine the temperature throughout the whole circuit. This is a finite element question, which is very similar. In this case, there's some nice work of Bowman, Hendricks, and Vavasas, where they show that, in fact, you can precondition the finite element matrix you get with a graph Laplacian, and thus you can solve it in near linear time. So other places this comes up is suppose you're interested in a random walk in a graph. So then where the random walk is given by a graph, symmetric graph, then in fact in this case it's not too hard to see. Classic results say that the mixing rate for this is related to the fundamental eigenvector of a graph Laplacian. And Spielman and Tang in their 2004 paper pointed out that in fact by using inverse powering, so in other words you solve linear system log n times, graph Laplacian, you actually get the eigenvector. Okay? So this says that this problem then can be done quickly, and we've used this. It works very well. Okay? So another way you can think of it is you can view your graph as a weighted graph, but now you, instead of the weights being conductors, those are springs, and so now you have a big spring system, and you're looking at modes of vibration of this spring system. Okay? And again, what you can show then is that the eigenvectors for this system here correspond to the fundamental modes of vibration of the spring system. Super classic stuff, right, from physics, right? But again, then, you can compute these fundamental modes, And this actually, we'll talk about this for image processing, for you can do image segmentation, no other way to think of this, okay? So again, you can do these using graph Laplacians, right? Another sort of fun application is this one of Tut. So here what you'd like to do is say compute the planar embedding of a graph where for some magic reason it is three connected, you happen to know an outer face. If you pin down that outer face and view all the edges in the graph as springs and you look at the low energy state of that, that actually gives you the embedding of the planar graph. Okay, so that's another sort of application. Okay. So other applications from the learning theory. So you can have graphs for which you have labeled and unlabeled graphs, and there's a collection of results that show, again, these things can be reduced to symmetrically diagonally dominant systems. Okay, so good. So what I've done so far is I claim I've shown you applications which use directly symmetric diagonally dominant systems. From a high level point of view, they said that you can use the fact that these are minimizing the L2 norm. If you're doing electric current flow, when you ask for the minimum current flow, you're asking for an L2 solution, right? And it says L2 is easy. But out in the world, there's a lot of beautiful applications that are not L2, they're L1 or L infinity. And probably the classic question is that of max flow. So what you're given in this case is you're given a graph, you're given capacities on the edges, and you're given two special nodes, S and T. And what you'd like to do is output the max flow from S to T subject to the condition that for all non-ST vertices, the flow in should equal the flow out. Notice I claim this is a Laplacian constraint, and so we should be halfway there in being able to solve this problem because one of the main constraints is already a graph Laplacian, okay? But the other constraint is not. It's an L infinity constraint, which says that the flow on any edge, the max flow on any edge should be less than the capacity. That's not an L2 constraint, it's an L infinity one. So then how do you solve these kinds of problems? Well, there's some beautiful theory that has come out, right, for doing this. One is Karmakar and all the derivatives of that on using interior point methods, okay? So what did they prove? Beautiful result. And they said that if you have M constraints, you can actually find primal dual solutions, and the runtime of that ends up being roughly the square root of the number of constraints. That's how many iterations you have to do. But unfortunately, each iteration requires you to do a linear system solve to determine the next direction you have to go. Okay? So the problem now is this gives you great algorithms if you can figure out how to solve the linear systems quickly. So what I claim then is that for certain kinds of problems like the max flow, sort of the first nice result in this direction was by Dash-Spielman, who showed that the max flow and also min-cost max flow and lossy generalized flow and a bunch of other variations of this all can be done quickly. And the reason is because each step then requires you to compute a Hessian. Hessian magically, because we had a Laplacian constraint in there, is some perturbation of a Laplacian, and so that each step then can be done quickly. So this gives you then a m to the 3/2 algorithm for the max flow problem, which matches the state of the art in just regular flow and is, I think, the best known for min-cost flow. Okay, good. So this is another application of why you want to do graph Laplacians. Whoop. Okay. So what's interesting is that if you're willing to have max flow in the undirected case, you can do even better. Okay. So far what we've done is the big hammer we applied then was the interior point methods. There's now becoming a whole theory algorithm design technique in the theory community called multiplicative weights. And the idea that, and so one of the nice applications, so this is a slide, I missed a slide. Let me do this one other quick slide, and that is if you want to do, for instance, computer random spanning tree, Kellner and Madre also showed how to do this. Okay? And also another application is, I guess there was a bunch of these I missed, was for image denoising. Classic question that comes up is you have an image and you have two terms. S is your image. You want to compute a smooth image X, so it should be close to the original image. You have a fidelity term. In this case, it's an L2 term. And you also want it to be smooth, but with an L1 term. And again, and you can do non-uniform versions of this. So again, so this can be solved in basically m to the 3/2 time. And again, what you do is you just throw at it log barrier. Notice that at each case in your solve, you have a low rank perturbation of a graph Laplacian, and so therefore you get the same kind of runtime. So again, it works. Okay, good. So this is where I was. Sorry. So going back, so there's this idea that you can actually do better on these algorithms, right? We don't believe that I mean, most people that do interior point don't actually believe that they should be paying the square root log n for, or square root of n term for the number of iterations. So, but there has been some work on getting around that, at least in the special case of max flow. And so this work on the special case where the max flow problem now is an undirected graph rather than a directed graph. And now the error term here is not log 1 over epsilon, which would be much better, but a weaker error bound. Then you get a runtime now, which is m to the 4/3 n. So this is a major breakthrough that in fact, actually, we've been able, that people have been able to get runtimes now that beat the m to the 3/2 runtime. Again, no one believes this is the right answer to this problem. That the answer is clearly should be linear. They know of no counterexamples to this. But anyway, this is sort of a major breakthrough in being able to apply this to this problem. Okay? So the question is again, so what happens, who cares about undirected graph flow? And there is sort of at least one very beautiful application, and that is for the question of the sparsest cut in a graph, right? So you have a graph, and what you'd like to do is remove a small number of edges to split it into roughly 2 equal sized pieces, sparsest cut. And for many reasons, people believe the best approximation is square root of log n. But of course, the question is you'd like to compute that quickly. And so this gives the best upper bound for that. Then you apply this hammer, and then you get a m to the 4/3 sparsest cut. Okay? So what I'd like to do is shift gears now and talk about the question of how does these solvers work. So let's just go back to iterative methods 101. So suppose you want to solve a linear system ax equals b, and you want to do it iteratively. The idea is very simple. You do what's called Richardson's algorithm. You start with an initial guess for the solution, say 0, the all 0 vector. Then you can compute how far you're off from that, the residual term, b minus a u to the I, ui, and then you add that error to your guess, and you update, and then you keep going, and then it's pretty clear that if you ever hit on the right solution, if you ever get a fixed point, you will have a solution to this system. Unfortunately, this may not converge. If it does converge, it may not slowly. So what do you do about that? Well, there's a bunch of things. There's conjugate gradient, Chebyshev, and a bunch of other things. Let's not worry about that trick. But the other major trick is what's called preconditioning the system. Notice we multiply our linear system on both sides by an invertible matrix. Then we haven't changed the linear system. But now we can think of this as an iterative method, because what we'll do now is we'll compute our residual error, and then we'll do a solve for b at every round, and we'll update our solution. And hopefully it should have two effects, right? We'll still get a solution, but hopefully the cost of computing these inverses at each round and will not dominate the fact that we've hopefully got fewer iterations, right? Okay? And then of course, as we all know in theory, once you have a good idea, then you should do it recursively. So if you then throw recursion on top of this, then you get one of these modern systems. Okay? Good. So now the question is, what should we use for our preconditioner? Well, it probably should be a Laplacian so we can do recursion. So we'd like it to be close to A, right? So clearly we could always make b equals A, and then we'd only do one iteration. But of course, we also want it to be the case that b is easier to solve than A. Well, one definition of easier is that it's smaller. So what we'll do then is we'll go and try to find a b which works, but is somehow smaller. Okay? And the next two definitions of smaller would be fewer edges and fewer vertices. Okay? So but people have looked at different a's. If you go back historically, people have usually used matrix variants, right? Jacobi used diagonal, and there's a bunch of others. But Vijay's main thing that he brought to this thing was he said, it's a graph, so what is a good subgraph of a graph? Well, if you look at any book on graph theory, it says spanning trees are not a bad start, so he proposed a spanning tree. Okay? And then, of course, we said, well, maybe how about a Steiner tree? But there was another clever idea that came out, and that's to use a low-stretch spanning tree. So I claim one thing, if you teach graph algorithms now and then, you should, the idea that we use max weight spanning trees as anything because it's easy to compute, it's not clear we ever want them. I claim that one should go back and make sure that you really care about that a max weight spanning tree is what you ever wanted. Low stretch, very interesting idea, so we'll talk about that again. And then in a planar case, then you could use separators because those are easy. Here what we'll do, and then the final algorithms will only use the low stretch spanning trees to approximate resistance. Okay? Good. So how do you get a good preconditioner? So what we'll do is we'll use random sampling in the graph B to reduce the number of edges, and then we'll sparingly use Gaussian elimination to decrease the vertex count. So the two of the steps are going to have the effect of, one, the first step is going to reduce the edge count, the second step is going to reduce the vertex count, and that'll give us our smaller problem. Okay? And I'm being very fast, so you won't probably follow all that. But anyway, good. So there's a very idea of Karger and Benziger-Karger on how you sparsify a graph. Very simple idea. What you do is you determine, by some secret sauce, a probability, P sub E, for every edge, and you flip a coin for every edge with probability, P sub E, okay? And if it comes up heads, you keep that edge, but you replace it with an edge of weight 1 over P. And you repeat this about log n times per edge. Okay? And this is a classic idea of how you could then sample a graph. Okay? So let's just apply it here for fun. So what we'll do now is take the complete graph and we'll sample these edges using this, and this is the one we get. And what's interesting here, I didn't actually do this up, is that every time I compile this tech code, it gives me a different answer, right? So the one on the right then is a sparse version of the one on the left. So notice two things happened here. It has much fewer edges, but the edges have heavy weight to make up for the fact that there's fewer. Okay? And this is called the sparsifier of this. And this is also known as a PNG, GNP graph, right? Good. Okay? So the only trouble is if we only had to do complete graphs, we're done. Unfortunately, we want to solve all graphs, right? So what do we do this? So anyway, so Benziger-Karger uses this for sparses cut. Okay? At a point here then, what happens is the expected value, the number of edges it goes down, but it still has a log in it, and we get concentrations, right? Good. Okay. So now what I would like to do is just go back and ask the question, how are we going to figure out the probability for which we should sample edges? And there's an amazing result on this, right? Very beautiful. And that is what we do is we consider every edge of our graph as a conductor, and we look at the effective resistance between those two nodes in the graph. In other words, we take a multimeter, and what you do is you measure the resistance between two nodes, the endpoints of an edge, and that magically is going to be the probability that works. Okay? Good. And this is a result of Spielman and Srivastava. They said that if you use these probabilities, in other words, and you weight it by the edge weight, okay, and that you get about n log n edges, and the condition number, whatever the heck that is, between these two graphs is very small. Okay, so they're very similar graphs. Good. So this is an amazing result. Just hard to believe that that happens to be magically the right number to pick. So everyone understands. So you have this big graph, and you're going to do this sampling trick, and you want to know what probability you should sample edges, and it's the effective resistance between the ends. Okay?
Where all the edges have equal resistance.
No. So in the complete graph, the effective resistance is going to be a very, very small number because it has all these other paths to get there.
No, but each edge has the same resistance.
No, it's in the whole graph. Right. So there's a slight. I see that I missed a very important point, and that is if your graph is highly connected, the effective resistance between 2 points is going to be a very small number. Okay? And if there's only that one edge in there, then that effective resistance is going to be 1. So you're just going to keep the edge. Okay? But clearly, if you didn't get it, I must have lost a lot of you. But anyway, okay. But the slight problem is, how do you compute effective resistances in a graph? Well, you solve graph Laplacians. Well, that's a terrible problem, right? Now we have this terrible catch-22, and that is we found this perfect way to figure out how to sample graphs and get rid of edges. But unfortunately, it requires us to solve linear systems, but that was our goal. So we're in a bind, right? So how do we get around this? Okay? So what we're going to do then is we're going to just do a sloppy calculation of effective resistance. And the way we're going to do that sloppy calculation is what we're going to do is use what we call low stretch spanning trees, right? So we'll say that the stretch of an edge in a tree is simply the length of the path between the two nodes. More formally, right, you take the effective resistance in the tree. Okay? So what we'll do now is we'll take a spanning tree, and now if you have any non-tree edge, computing the effective resistance can be done quickly, but unfortunately it'll give us the wrong answer. Okay? But it'll be good enough, and that's the trick. Okay? So this idea it comes up in all kinds of sparsification results. Okay? So the interesting question then is, I'm sorry. So that we say that a spanning tree has low stretch if the sum of the stretches is small, right? So this is sort of like what I would call an L1 spanning tree, right? It says that you pay for just the sum of all the stretches. So this is a spanning tree that has good L1 property, okay? And so this is used for all kinds of sparsification results. And this is a beautiful history, right? So originally it was some work of Alon Karp-Peleg-West, where for K-server, totally unrelated problem. This then became a high art, and there's very hard papers that show how to compute the stretch. And notice that the state of the art is m log n, which is tight even for simple square meshes. So that you can quickly then compute these low stretch spanning trees. It's a very high art, and unfortunately it'd be nice to have actually practical algorithms for this, but it says that it's doable, right? Good. So just to make sure you understand, the idea here is suppose you take the square mesh as your graph, and what you do is as you do a recursive C construction, then this red graph here has low average stretch. So this is an n log n stretch for the square mesh. And the reason is most of the edges are going to have very short paths between the n, but now and then they will have to go through long paths. And so that's what happens, right? Okay, so this is a low stretch spanning tree. Good? Okay. So now what I like to do is just, because I don't really have time to properly go through this whole algorithm, is just run our preconditioner algorithm on the simple graph. So this is the original system you want to solve, and then how we're going to do this. First, we're going to go out and generate a low stretch spanning tree, say this red one. Then what are we going to do? We're going to do this trick of increasing the edge weights on the spanning tree and making them heavy. We're going to pay for that in the preconditioner. So now B now all of a sudden picked up some heavyweight edges. Okay. And then what we're going to use is those red edges to compute the effective resistance of the black edges, okay, that are remaining. And we're going to sample those. And so after we sample those, we're going to get fewer non-tree edges, and that's this. And now we're going to apply Gaussian elimination to remove all the degree 1 and 2 nodes. So that's the sparse. And now this is then basically the preconditioner for that original matrix, right? So we go back, right? So you wanted to solve this linear system, right? You compute a low stretch spanning tree, you make it fat, you sample the non-tree edges, you get a few, fewer edges, and now the graph, if it's sparse enough, is going to have a lot of degree 1 and 2 nodes, and so then you can pivot those out without affecting your edge count. Okay, so you remove those, and that's the solver. Good. So we do have code we haven't actually implemented some of this. The low stretch spanning tree is a problem, but in the planar case, we have implemented this. This is actually an interesting question that the theory community has been working on planar linear system solvers for a long time. There's conjugate gradient, nested dissection in the 70s, combinatorial preconditioners, Vija's in the 90s, low stretch spanning trees, and then some separator-based stuff. But it all comes down to what's interesting is that it actually works pretty well. So we've coded up a variant of the solver, and it looks very linear. If you run it against other versions, say MATLAB, they run out of memory, especially in 3 dimensions. And and again, this is a problem. Okay. So what I'd like to do is just talk a little bit about how to use a classic application of this stuff is for image segmentation. So what you do is you, in this case, shifting gears here, is I want to then do graph partitioning using spectrograph theory. So what you do is a basic idea. You compute a few low frequency eigenvectors, and you use these to embed the graph. So I did this in this example. So you have on the left a regular embedding of some planar graph, and you've written this in terms of a couple eigenvectors on the right. Okay? And then she and Malik proposed to use this for image segmentation. So here's just a simple image. When you actually apply it directly, you don't get very good things. This is is called the blue sky problem. You end up getting vertical cuts when you really didn't want it. So we came up with some ideas. Doesn't completely always work, but it does dramatically better, called spectral rounding for doing this. And the basic idea is very simple. Oh, I wonder what that is. I don't know the password. If I knew, I'd put it there. Okay, what you do then is you do sort of a reweighting algorithm. You simply solve for your eigenvector, a generalized eigenvector. Then what you do is by a magic sauce, you reweight the graph, and then you recompute the eigenvector and repeat until lambda 2 goes to 0. Okay? I think this is going to work. Not sure what happened. Oh, well, so. Okay, so in fact, actually, what's interesting is a method that works very well is what you do is you simply do gradient descent. You simply look at the partial derivative of lambda 2 with respect to the edge weight, and that gives you a good way to do it. So here's a couple examples. I have this on automatic for you, and this segmented some breast tumors. Okay, so. And that's my talk. I think someone here is helping me do this talk at the end.
Okay, question?
Yeah.
So earlier on, you talked about an application to machine learning where you were looking at a graph and then the neighboring points. Could you just show how that's related to the theory just one more time?
So this is the stuff about like Lafferty and Greer, right? That I don't understand as well, right? So somehow magically what they do is they take even, the simple case would be where you have labeled data with undirected graph, just a simple affinity. And then that would look very similar like the spectral type partitioning, right? And what they were able to do is to somehow generate an undirected version but still keep in the class of graph Laplacians. Okay?
I'll be your straight man. What's the story of the breast cancer thing? I didn't get how that fit in.
So the thing is this is supposed to have some things from the field, and so doing a little image processing for breast cancer was supposed to be the little thing about stuff in the field, right? No, but what I was saying there was that if you use spectral methods for doing the image processing, it ends up doing a nice job in the sense that is this thing going through that? You get the whole talk twice. Hey, they're not going to stop me. I'm going to have the whole talk run twice. But so the idea is that magically using spectrograph theory, you can actually do a very nice job of segmenting images, right? And the trick seems to be one of these multiplicative type reweighting algorithms. Seems to work very well, or steepest descent. Okay.
So can you extend some of this theory to positive definite linear?
Oh yeah, so that's a very hard question, right? So unfortunately, the way to think of these, the other way to think of these matrices is that they're the sum of these little matrices, which are 1, -1, -1, 1, right? The little 2 by 2 matrices. That's what these graph Laplacians are, right? And even if it's a sum of 3 by 3s that are nice, it's not known how to do that, right? So the one result I did talk about, the Bowman-Hendrickson-Vivacys, if that little 3 by 3 matrix has a property that it's of rank 2 in a way, in some sense, then they can do it by preconditioning it with a bunch of rank 1, with a bunch of 2 by 2 matrices. But it's wide open how to do symmetric diagonally dominant systems, right? That's one of the beautiful open questions, right?
Symmetric positive definite.
Positive definite, yeah.
So the technique works for undirected graphs. Theoretically it doesn't work for directed graphs. And I'm wondering if somebody has tried it on data, or is there a lower bound for directed graphs?
No, there's no lower bound, right? It's wide open, right? We don't even know whether you can't solve all linear systems in linear time, right? I mean, that may still be possible, right? Maybe you don't need any of this stuff, right?